Mm. Uh, Hi Tony, today we start the sequences. So first we'll get to the terminology of the sequences. What are these? First we'll study what are these. So sequence is nothing but a what do you how do we generally find the sequence? That means a row of numbers, right? So let's say 2, 3, 4, 5, 6, and so on up to let's say 10,000. This is also a sequence of the numbers, but what we study here is the sequence of infinite numbers. Let's say first one we represent in the set form 3, 4, 5, 6, and so on. It goes up to the infinity. So this is one example of the sequence, and as far as basic definition refers, as sequence is an ordered list of infinite numbers. An ordered list of infinite numbers. Okay. For example, we see some of the examples. Ordered list, that means what does that means? First we examine ordered list, right? So what is this ordered list? U doesn't change its order. You do not change. You have you doesn't have the authority to change the order of that list. Do not change the order. You take the sequences as it is given to you. So while we examine some of the sequences, first one example we are given here 1, 2, 3, 4, 5, 6 up to so on up to the infinity. This is the sequence of natural numbers. Okay. For suppose for example, another example, if we give um, 2, 4, 6, 8, 10, and so on. This is another example of the sequences. Okay, this is called these are all the even natural numbers, right? So and if we go to the odd natural numbers, 1, 3, 5, 7, 9, and so on, you can continue like this. This is the sequence of odd natural numbers. mm, see on See here, there is in the above two examples here, the interval is even. That means difference between 4 and 2 and 3 and 1, any between any two terms of the above these sequences are difference is 2, but there is no restriction that the sequence has to maintain the same difference. So 1, 5, 6, 7, 21, 35, 1 or 2, it can go on. So the difference need not be the same. So it need not to maintain the same difference. This is also a sequence of the numbers. See here, the above three examples of the sequences are in a increasing mode. That means the second term of the sequence is greater than the first term, right? So this is all in increasing sequence of the numbers. So the sequence need not have to maintain that either increasing or decreasing. So we can give the one of the simple examples: 6 1 3 10 9 22 and so on. You can go like this, so no need to maintain that increasing or decreasing condition here. Okay, and we give, see this here, the sequence are all of different terms here, all the sequences. A sequence need not have to be all different terms. Let's say 2 2 2. A sequence may contain something like this: a sequence of 2's up to infinite number of 2's. Okay, this is also a sequence. Particularly this type of sequence is called constant sequence. Constant sequence, right? And if we go, so these are the some of the examples of the sequence, and we can give another example also. See here, all the numbers are the natural numbers here, but the sequence need not be a natural number. The domain with in which you are defining defines the terms of the sequence. So it can also be like a 0 1 2 3 and so on up to the infinity, -1 -2 -3 and so on. It can go to the minus infinity also. So this is a sequence of integers. This is a sequence of the integers, and we can also have the sequence of the real numbers like sequence of the rationals. We consider first 0 0.2 0.4 0.6 and so on. Here the increment is only the 0.2 increment. With this we can continue writing infinite numbers. So this is also be called a sequence. So it the conclusion is this: sequences does not have to maintain a particular order and a particular one. Okay, so it may have any possibilities. So these possibilities leads to a different types of construction, different types of terminology in the sequences method, sequences concept. So here we see that these are the increasing sequence. So we can have this a sequence which is increasing is called increasing sequence. Increasing sequences, and decreasing also can happen. So later we go to the formal definition of what is this. We will give a formal definition for what is increasing sequence and what is decreasing sequence. Later we will give that. So I'm giving you a rough idea about this one. First, generally, okay, we will go to the general analysis and representation of the sequence. So if we give the sequence, let's say uh, okay, we for suppose if a sequence of arbitrary numbers a1 a2 a3 a4 and a5 and so on, it is given, the sequence is given something like that. So we represent this sequence as ai, where I is an arbitrary term where I goes from 1 to infinity. Or else you can define a sequence something like this: a j. That's it. J, we, if it is called a sequence, you it is embedded that j goes from 1 to infinity. Okay, the normally the sequence can be represented in the terms of u or v, something like that. Okay, u is equals to ai, or they can simply give the sequence bi, where I goes from 1 to infinity, or they can it can be represented as bn, small n, so where n goes from 1 to infinity. Okay, so what this sequence is, as you can see that a sequence is nothing but a, see here, sequence is see in this example, see here in the, let's take this example 1. So in the sequence 2 4 6 8 10 12 14 and so on, see this is the first term of the sequence, and this is the second term of the sequence, this is the third term, this is the fourth term, this is the fifth term, sixth term and so on. So if these terms, see 1 2 3 4 5, these the term of this does not change for any sequence, right? This is the first term, this is the second term, this is third term, fourth term, fifth term, sixth. So then term does not change where n goes to 1 to infinity. That means here this n belongs to the natural number set, capital N. If we can define the sequence something like this: sequence is a function, so the sequence is a function from natural number set to any, we can generally call the real number set. Sequence is a function from natural number set to real numbers, or you can also define the codomain as the complex number set. Okay, the if the codomain is natural number, then the sequence is called the sequence of natural numbers. If the codomain is complex, then it is a sequence of complex numbers. Okay, so this is the basic fundamental definition. Sequence is a function from natural number set to the real numbers. Here we discuss only the real numbers, because if we study the real numbers, the complex study of complex numbers is also the same. It doesn't differ much. So this is a formal definition as a function. Okay, next we go to the terminology, some more terminology of the sequence. So what is the terminology? Let's say if we take the sequence a1, a2, a3, a4 and so on, if we take our sequence something like this, see this sequence u, let's say the sequence u is given something like this. See that each a1, a2, a3, a4 are called the terms of the sequence. So in generally you can define it as a I is the term of the sequence. And here I is the index variable. Index variable. Okay. In sometimes AI is also can be represented as an. So the index variable can be changed, but this is the widely used notation in many textbooks. So we follow this one from here. AI, see, it can be represented as AI and AJ, AK, or whatever it is. So index variable can be changed. And so what is this? Now we define the sequence as a function, right? Sequence is a function from the natural number set to the real numbers. So we see what does its how does it can be represented graphically. For example, if we take a sequence of even numbers, even natural numbers 2, 4, 6, 8, 10, and so on. See, this is the first term of the sequence, this is the second term, third term, fourth term, fifth term, right? So if you combinedly write n and f of n, okay, in a tupled way, that means in a tuple way, then we can able to point out those points in the graph. So first term of the sequence, above sequence is 2, so 1 2, and second term of the sequence is 4 2 4, third term is 6, fourth term is 8. It can continue like this. So when you graphically put that means note these uh, points. So this is 1 and this is 2, so we have a point here. Let's say this is 2, 3, and 4. 2 3 4 5 6 7 8. So we have 2 to 4, 2 4, this is another point here. 3 6, this is another point. Next the point is 4 8. Okay, that points in the sequence can be represented like this. Okay, so there can be a function which joining the all these points of the sequence. That can be another function. Okay, so we will discuss about those functions which, see, there is a line joining all these points. Like we know y is equals to 2x. That is the line that this is the line that containing all the points of the sequence. So for now we can know that there exists a continuous function, a continuous function that contains the given sequence. Okay, so as it says that if we give a sequence, we can find a continuous function which does contains the sequence points of the sequence. Okay, here it says particularly a continuous function. We can have, they does not define a function, but they defined as a continuous function. So this is so particular. So there exists a continuous function, right? um okay, so we discuss this concept in detail later. Oh, Okay, with this the terms of the sequence is, we know that what is the term of a sequence, what does the I means, the index variable. Okay, so a sequence need not follow a pattern. Okay, normally when the problems are given, it follows a particular pattern, that means a particular generating term. Okay, here the sequence an is the number an can be, an is any arbitrary number in the sequence. It can be acted as the general term of the sequence, general term of the sequence. So okay, so we, if we give a particular okay, next problem, and the if so if we give any sequence, so we try to find the general term of the sequence. mm, okay, let's see, let us give some examples here. Okay, for suppose if I give, for example, okay, example, I give the sequence as minus half, 2 by 3, minus 3 by 4, 4 by 5, minus 5 by 6, and so on. So can we able to find the general term of the sequence? For suppose, see, when you observe this one, the numerator of that any term of a sequence is 1 less than the denominator. So our general term an is n by n plus 1. And for odd terms, see, this is the first term, third term, fifth term. For the odd terms there is a negative sign. How do, for the even terms there is no negative sign. This can be produced simply by minus 1 whole to the power of n. So this is the general term of the sequence, and this entire sequence can be represented by minus 1 whole to the power of n into n by n plus 1. Okay, with the general term we can define this sequence something like this. Okay, if we observe the second example here, second sequence is given as, okay, the second example given as 3 by 4, 9 by 7, 27 by 10, and 81 by 13. Okay, 243 by 16, yes, and so on. See here, all the numerators of this sequence are uh, power to the 3. Okay, this is 3 power 1, this is 3 square, 3 cube, 3 to the power of 4, 3 to the power of 5, and so on. All the denominators you see, this is the denominator of the first term. You try to generate the denominator in terms of 1. So we have okay, 3 plus uh, no, we try to generate in terms of 3n, 1 plus 3n. Okay, so this one, see, this is fourth is 1 plus 3, the 7 is 1 plus 3 into 2, the 10th is 1 plus 3 into 3. So we can generate 1 plus 3 into 1. This is the first term, second term, third term. So the general term for the denominator is 1 plus 3n, and the numerator is 3 to the power of n. So the general term an is 3 to the power of n divided by 1 plus 3n. We can give the sequence something like this. Okay, if you want some other example, we can have that. Okay, let's take some of the, you try this one. What do you find the general term of this sequence? 1 by 5 minus 1 by 7, 1 by 9 minus 1 by 11, and so on. Find the general term of this sequence. You can take this as a homework. Okay, so next we study, so is the concept of the sequences is new to us? Is it new? We have a question here. Is this concept is new to us? Aren't we study the sequences before? In the previous classes anywhere? The answer is we studied these sequences previously in by the way of progressions. That means in the name of progressions. We know we studied arithmetic progressions. Okay, arithmetic progressions and geometric progressions and another progression we also studied. There are so many kinds of the progressions, and this arithmetic progression is we widely studied these two, and another one also we know I unable to remember the name. So arithmetic progression, this the difference between any two consecutive terms of the sequence if you taking these progressions to the infinite number of terms. Okay, normally the progressions can be a finite terms also. If we take it to the infinite, this is a particular type of the sequence, and arithmetic progression is we is nothing but the difference between the consecutive terms is same. That means is same between any two consecutive terms. Geometric progression, that means the ratio between any two consecutive terms is same. Okay, so we so this concept is not new, but we studied in a different form. So can we find uh, see here, if we give any general term of a sequence, so general we can develop a sequence from there. Okay, for suppose if I give a sequence like 1 by n, that means you can generate a sequence n goes from 1 to infinity in the denominator, so it can be 1 by 1, 1 by 2, 1 by 3, 1 by 4, and so on. If we give the general term, you can generate the sequence. So 1 by 1 whole to the power of n divided by n. The sequence is nothing but minus 1, 1 by 2, minus 1 by 3, 1 by 4, and so on. Another example can be 1 minus 1 by 2 all to the power of n. If you are if you can write so many examples, that would be very that would give you a deeper understanding of the sequences. So it is 1 minus, if n goes from 1 to infinity, so it is 1 minus 1 by 2, 1 minus 1 by 4, 1 minus 1 by 8, 1 minus 1 by 16, and so on, right? So let's say if e to the power of n, this is also another sequence, e square, e cube, e to the power of 4, and so on. Okay, so now we study some of the specific example of the sequence, and we try to what do you say, that obtain a particular concept. Okay, so what is that concept? When you generalize, when you study the particular examples, we will able to know what is the concept there. Okay, so first we study the sequence of 1 by 2 to the power of n. Okay, let's say it is example 1, 1 by 2 to the power of n, the general term of the sequence given as this one. Okay, so this means the terms of the sequence is like this: 1 by 2, 1 by 4, 1 by 6, 1 by 8, 1 by 16, and so on. Okay, so in this, let's say when n is equals to 1, this is 1 by 2. When n is equals to 2, 1 by 4. N is equals to 4, that is 1 by 16. Okay, so when n goes to the infinity, what is the infinite term will be in this sequence? That means if you find the limit, you can find what the sequence is approaching to. Let's say that is called limit. Take the limit n tends to infinity, 1 by 2 to the power of n. Find out what it is. 1 by 2 to the power of infinity. This is a very crude way to solve this one. That is 1 by infinity 0. Okay, so the infinite term, the end term of the sequence will be the 0 here. So this, all the terms of the sequence is gradually approaching to the 0, right? So this 0 is called limit of the sequence. What do you call this? Is called limit of the sequence. Let's see another example. The general term of the sequence is given as n. So this sequence is, when n is 1, it is 1, 2, 3, 4, 5, and so on, right? So try to find what the sequence is approaching to. When the limit n tends to infinity, n is nothing but infinity. So the sequence is approaching to the infinity. This is also the limit of the sequence. Okay, limit of the sequence, right? This limit, see here, you obtain a finite limit here. See, you obtain a finite limit here, but you are obtaining an infinite limit here. So this, when a sequence is approaching to a finite limit, this is called, such sequence is called convergent sequence. convergent sequence when any sequence is approaching to the infinite limits, whether it is positive infinity or negative infinity. We call such sequences as divergent sequences. Divergent sequences. Okay, there are some sequences which does not converge, or neither converges nor diverges. So we'll see what one of the example of such sequence is minus 1 whole to the power of n. If you write this sequence, this is nothing but minus 1 plus 1 minus 1 plus 1 and so on. You can keep going. You cannot define what is the sequence is approaching to. The sequence is neither approaching to the negative one nor approaching to the positive one. If you say the nth term of this sequence is negative 1, the next term will be the positive one. So this sequence, you cannot say anything about it. So we call these such sequences as oscillatory sequences. Oscillatory sequences, right? So we, in the oscillatory sequences, we study another example. Let's say these are the classical and simple examples we give here. In the problems, we analyze and study and we solve some of the complex examples, right? Let's say minus 1 whole to the power of n into n. So this means it gives minus 1, 2, minus 3, 4, minus 5, 6, minus 7, and so on. See, when this the end term of the sequence is an even term, if the sequence is continuously approaching to the infinity, if the end term is even, you approach to the infinity. If the end term is odd, you approach to the minus infinity, right? You cannot say whether the sequence is approaching to infinity, positive infinity or negative infinity. So this is also an oscillatory sequence, but it does not have a finite oscillations, it does have an infinite oscillation. So you call such sequences as oscillatory sequence oscillating infinitely. So this is there are two sequences, as you can see in oscillating sequence. There are two types: finite oscillation and infinite oscillation. Okay, so example 4 is the infinite oscillation, and example 3 is having the finite oscillation here. Okay, a sequence which neither converges nor diverges is an oscillatory sequence, right? And we already defined another definition here, the limit of the sequence. So how do we find that the limit of the sequence? This is the limit of the sequence. So when you find the limit of the general term of the sequence, you can find the limit of the sequence. So using that, we can define different how the algebra of convergent sequence behaves and divergent sequence behaves. Okay, let's say the okay first we study the convergent sequences behavior. Okay, so but in we know from the concept of the limits. Okay, from a limit n tends to infinity let's say limit of the function fn is L and limit n tends to infinity gn is g of n, let's say f of n, we defined as a function, it is m, then there are some algebra of the limits. Okay, what is its sum behaves like, what is its product behaves like, let's say, so the limit n tends to infinity f plus g of n is nothing but it goes to the L plus m. Okay, if L and m are finite, L and m are finite values, and f plus g we can give another negative also here. If f minus g of n can approach to the L minus m. Okay, so in the same way f g of n can goes to the L into m. F divided by g of n can approach to the L divided by m, where m is not equals to 0. In the similar way, for suppose c is any constant like a 0.2 or 0.3, whatever the constant you can take, c into f of n approaches to c into L. This goes same with the function g also. Okay, so as you can see here, and the function from here you can say the limit of 1 by g is nothing but 1 by m, where m is not equals to 0. If m is not equals to 0, the limit of 1 by g of n goes to 1 by m. Same, the algebra of the limits can be applied in the case of the convergent sequence, but not in the case of the divergent or oscillatory sequences. They fail in remaining types of the sequences. They fail to hold the limits. Okay, the convergent sequence. Let's see what is that means. Let's say a sequence an converges to a, and a sequence bn converges to another number b. That means if you combinely write, that means term by term addition of these two sequences an plus bn, that means first term of the sequence, first sequence and second term is added, then this term by term addition generates another sequence. That one is this converges to a plus b, and if you can have term by term subtraction, a plus minus bn gives to the converges to a number a minus b. Same goes with the multiplication also, an into bn converges to a into b. Same with the division also. Here the division, in the division you specify that b is not equals to 0. Okay, c into an, where c is another constant, converges to c into a. Okay, and 1 by an, this sequence converges to 1 by a, where a is not equals to 0. If a is equals to 0, then this sequence diverges, does not converge. Okay, So if these two are finite, where you specify that these two are finite numbers, finite limits you can say, then this holds. This last does not hold. Let's say this is law 1, 2, 3. They do not hold in the case of divergent sequence or oscillatory sequences. Why? Because we'll see, we can have some such examples here. For example, if we take two sequences, divergent sequence, okay, -1, -2, -3, and so on. See, the sequence diverges to minus infinity. We can have another sequence 1, 2, 3, and so on, diverges to plus infinity. So if we add term by term of these sequences, you get 0, 0, 0, and 0. So this sequence converges to the 0. We know that. But if we apply the same laws that we learned in the case of convergent sequences, we must have minus infinity plus infinity. But this sequence is converges to 0. So minus infinity plus infinity is undefined, infinity minus infinity, so is an undetermined indeterminate form. So this need not be equals to 0. Okay, so that's in this case of divergent sequences, the laws, limiting laws of limits fails here. So I try to give one more example for the oscillatory sequence. Let's say we have an oscillatory sequence 1 -1 +1 -1 and so on. So this is minus, let's take another oscillatory sequence -1 1. If we add these two sequences term by term, we get a constant sequence of zeros. So this sequence converges to the 0. This is an oscillatory sequence, and this is also an oscillatory sequence. Okay, so but this is not an oscillatory sequence, but it converges to the 0. But you cannot generalize that sum of two oscillatory sequences is sequence converge. You cannot say that. This is one, that means I'm giving the examples just because you must know that sum of two oscillatory sequences need not be oscillatory. Okay, and now we see in the case of infinite oscillations. Okay, you can also see that you can make some of the oscillator sequences, you can make this as oscillating finitely, infinitely. So you use two oscillatory sequences to make it a convergent, to get a convergent sequence. You can also do with the oscillatory infinite oscillations. I am leaving that case to you. Right. Okay, first we solve some of the examples here, finding the limits of some sequences. Okay, first we give, okay, the formal definition is in the book. You can check it out for the limit of a sequence. We'll solve some of the examples here. This is the sequence given. You can see the general term of the sequence is given here. So if you find the limit of the sequence, limit n tends to infinity, 5 minus 3 by n square. See here, this n, when you substitute infinity in the place of the n, so what do you get? 3 by infinity, that is 0. So you get 5 minus 0 is 5. So this sequence is converging to the 5, converges to the 5. Suppose another sequence is given, 3n to the power of 4 minus 7n square plus 5 divided by 6 minus 4 n to the power of 4. What is this going to? Is this converges or diverges? Find its limit. Limit n tends to infinity, 3n to the power of 4 minus 7n square plus 5 by 6 minus 4 n to the power of 4. You divide both the numerator and denominator with the n to the power of 4. Okay, the n is not at infinity, so you just divide that. We get limit n tends to infinity, 3 minus 7 divided by n square plus 5 divided by n to the power of 4, n to the power of 4. You can say this, n to the power of 4 all divided by 6 divided by n to the power of 4 minus 4. Now you directly substitute what is n. So in the numerator, 7 by infinity, 5 by infinity, both of these terms is going to be 0. Here in the denominator, 6 by infinity, this is also going to be 0. So what do we remain is 3 minus 0 plus 0. And this is 0 minus 4. So we have minus 3 by 4. Okay, so the sequence is converges to minus 3 by 4. You can say that. Now we see another sequence, 2 to the power of n by n square. See here, you see this is a very particular one. We use previously studied knowledge here also. So find the limit of it first. Limit n tends to infinity, 2 to the power of n by n square. See here, 2 to the power of, if we directly substitute, 2 to the power of infinity is infinity, infinity square is infinity. So it is in the form infinity by infinity. Now what do? You use L'Hopital's rule. L'Hopital's. L'Hopital's or L'Hospital's rule, whatever it is. So first you differentiate this one with respect to the n. Like what is the differentiation of 2 to the power of x? It is 2 power x into log 2. So you differentiate the numerator and the denominator separately. So it becomes 2 to the power of n log 2 divided by differentiation of x square is nothing but 2x, right? You consider it as 2 into n. So again this is in the form of infinity by infinity. You need to differentiate again. So if you do that again, limit n tends to infinity, 2 to the power of n log 2. Already this is a constant. In the differentiation you pull the constant out of the differentiation, that constant will be appear log 2. So same goes here, that is 2. Differentiation of 2x is nothing but 2. So we are doing here the differentiation with respect to the n, with respect to n. So we do something like that. Okay, so limit n tends to infinity. Now we can apply here. See, this is log 2 whole square divided by 2. log 2 whole square divided by 2 limit n tends to infinity 2 to the power of n. This is nothing but infinity. So this is nothing but infinity. Infinity into some finite constant is also an infinity. Finite non-zero constant here. So this diverges. You can say that this one diverges to infinity. Okay. Can we able to solve one more problem? This is a similar concept which is very close to the limits concept. If you know the limits, then you can find whether it is diverges or converges, but it is not always possible to find using the basic concepts of the limits. We need some more advanced methods to solve this one. Okay. Now we have another example. We discuss those advanced methods, whether the sequence is converging or diverging. We need some of those advanced methods we study later. Okay. So for example here 1 plus 4 by n to the power of n, right? This diverges to, I say, whether it is, what is the limit of this one? This converges to e to the power of 4, I think. Let's find what is the limit of this one. Okay, it is given that 1 plus 4 by n into 4. How do you find the limit of such things? As I explained, we use the logarithmic. We take the help of the logarithms. It is n not 4. So let's say this limit is L. We apply the logarithms on both sides. We take log L here. Okay, log L, and we apply here logarithm. The logarithmic function is continuous, so the limit can be interchanged with the logarithm. So log can enter within the limits 1 by 4 by n whole to the power of n. Log x to the power of n can be written something like n into log something. Okay, so this n can be defined as log 1 plus 4 by n all divided by 1 by n. See this limit n tends to infinity. If n tends to infinity, if you directly substitute, this is going to be 0. Log 1 is nothing but 0. Log 1 plus 0 is log 1, that is also 0. Here 1 by infinity is nothing but 0. So this is the case of 0 by 0 form. This is another indeterminate. So what do is we differentiate both the numerator and denominator separately with respect to n log L. Okay, so what do you get if you using the L'Hospital's rule? If you differentiate the logarithm, so what do you get? 1 by 1 plus log x differentiation is 1 by x into, you need to differentiate what is within the logarithm, what within the function, that is 1 differentiation is 0. For the 4 by n differentiation is minus 4 by n square, right? And the differentiation of 1 by n is nothing but minus 1 by n square. Now you can see this negative and this negative. See, this is 0 does not have enough effect in the product, so this is, you can consider assume only this one. so you can cancel out these two, and n square 2. So what you have is 4 by 1 plus 4 by n limit n tends to infinity, right? That is log L. So when you apply infinity, the limit here, 4 by infinity, this is going to be 0, this term, and 4 by 1 is nothing but 4. So log L, here L is equals to e to the power of 4. Okay, so this one, the given sequence converges to e to the power of 4. So we can give some of the examples of this one based on the logarithms. See here, 1 plus a by n whole to the power of n. This sequence converges to e to the power of a. Similarly, 1 plus 1 by n whole to the power of a into n. This sequence converges to e to the power of a. Okay, I recognized using this general term, when if there is a in the numerator within, then that converges to e to the power of a. If there is a with the multiplication of the n, this converges to the e to the power of a. So I will give you some more homework later. Okay, so with this I will end the session here, and I will try to upload this video as soon as I find time. Okay, see you, Tony.